What I'd like to do is set up our first polar integral from an example and try to build how to build a polar integral, and then we'll look at the summary and then we'll try one more example. Meanwhile, we've got a function, remember, so this is the function, this is the roof, right? That's the cone, but I want the bottom, once we smush it, to be between the cardioid and the circle. Now, the problem with this is that we can't use regular French fries because there's no x's and no y's, and converting r equals 1 plus cosine theta into rectangular just sucks. So what we need to do is we need to use polar French fries. Now, what do I mean by polar French fries? So what I'm going to do is, let's just draw just the cardioid for the moment. I'll worry about the whole thing after that. Now, what I want, I have a roof up here. What I want is a teeny tiny base down here, but doesn't use x's and y's. Now remember how we made the little tiny rectangle on the bottom with x's. We held x constant, we held x a little bit bigger constant, we held y constant, we held y a little bit bigger constant. I'm going to do the same sort of thing here, right? I'm going to hold theta constant. Well, that's a ray. Then I'm going to hold theta a little bit slightly bigger constant. That's a slightly bigger ray. Then I want to hold r constant. Well, that's just going to be a piece of a circle. It's going to look like that. And then I'm going to hold r at a slightly bigger constant, and you get a piece like that. And you can see that this is going to be the base of our polar French fry. What I need to do is find the area of that base. And the nice thing about this is that we can take an estimate, because as we take the limit of the estimates, they all get bigger. So what am I going to do? I can see, for example, that this is actually a straight line and its length is delta r, so that's not a big deal at all. This little piece in here, that little piece of a circle, as long as delta theta is really, really small, that looks really, really straight, and we're going to get what really looks like a rectangle. And the problem is, how long is it? Well, if this circle was the unit circle, I don't know if you remember this or not, right? Delta theta would just be the arc length of that little teeny piece. But if it's a bigger circle, the length of that piece is actually r times bigger, and you get something that looks like that. So r delta theta is an estimate for that little piece right there. You might recognize that as the formula for arc length. But the area of the base then is going to be r delta theta. And that's just an estimate for the base. I'm not saying that r delta theta is equal to delta x delta y. Delta x delta y is the area of a base where we make rectangular chops and make rectangular looking French fries. We want polar looking French fries where the base actually uses r and theta, and that's actually what we're going to use for the area of the base. Now, meanwhile, we can actually start getting closer to building the integral. I know the double integral should have an integral out here, an integral in here. I know I should have a formula for the roof. I know I should have a formula for the area of the base. Actually, why don't we make sums and then we'll take a limit. We'll only have to do this once. We already found that the area of the base looks like r delta theta. So that's going to be the area of the base of the French fry. We already know what needs to go right here is going to be, that should be y squared, is the equation of the roof, but not in x's and y's. I do know that the square root of x squared plus y squared is r. So what I can do right here, instead of putting the square root of x squared plus y squared, I can just put another r. I'm happy with that. So that is going to be the volume of the French fry. I can stack them up and make a little piece of pie, actually, and then I can add up all the little pieces of pie. I take the limit as delta r goes to 0 and delta theta goes to 0. And what I'm going to get is a double integral, like we got before. I'm going to have r. The deltas turn into d's when we take the limit. So I'm going to get this. So this is actually when we do it this way. So that r is the roof. This is r dr d theta. When we evaluate this, we certainly can multiply them. But how am I supposed to find the limits of integration? Well, the way we found the limits of integration before is we looked at just in the xy plane, so it didn't involve the roof at all, and started drawing lines parallel to the x-axis or parallel to the y-axis, whichever we had to do first. We can't do that here because the equations of the x and y would actually completely screw this up. So we're not going to do that. We know that r's actually travel along rays while theta is being held constant. So whenever we find the limits of integration for polar, we draw rays instead of lines. So let's actually now draw the region. We're always going to have the region drawn. We might not have to have the whole solid drawn. There's our cardioid. There's our circle. We want the area between those two. So what I'm going to do is start drawing rays. And I want to know what is R as those rays enter the region, and what is R as those rays leave the region. So again, putting in our integral, we have integral, we have the R from the roof, we have the R dr d theta from the bottom of the polar french fry. You can see here that R enters the region at the cardioid, so that goes like this. This is going to be 1 plus cosine theta down here. You can see that R leaves the region at the circle, but R is always 3 up there, so I can put a 3 right there, which is good. And now I have to ask myself, what thetas was I using as I was drawing all those rays? Well, you can see that I needed to use all the thetas between 0 and 2 pi. Now, by the way, I could also go from minus pi to pi, as long as it actually goes all the way around the circle one, so we're good. So I'm going to get 0 here, I'm going to get 2 pi here, and there is our polar integral. It's our first polar integral. All right, on to the next example.